Hello everyone, thank you for watching my presentation. I am Lucas Stapper, a second-year PhD student working together with Michiel Hoogheide and Evine van Dishoek, and I'll be talking about my recently published paper about the massive planet-forming disks around Herbig stars as seen by ALMA. This is the star and planet forming cycle. It all starts in a diffuse cloud, which will eventually collapse under its own gravity and, because of angular momentum conservation, form a disk around the young star. In this so-called protoplanetary disks, planets will form, and the gas and dust dissipates eventually, and the planetary system is left over. In the past few decades, a large variety of exoplanets have been found inside of these the planetary systems, and we would like to know how these can form. ALMA has made it possible to do population studies on protoplanetary disks now as well. Here you can see one from the Lupus star-forming region, and we would like to know and to find out what the link is between these. One relation found from these population studies is that more massive stars have more massive disks. This plot here shows this relation for different star-forming regions, going from young to old. And for all of them, there is a clear increase in disk mass for stellar mass. Additionally, this relation steepens over time. In other words, the disk around more massive stars seem to retain their disk mass for longer. Also, a relation between disk radius and mass has been found. Larger disks are more massive. This relation flattens over time, and this suggests an evolution towards smaller disks. One major caveat, however, is that that in these population studies, early spectral types are lacking. While this is to be expected from the initial mass function, it does leave a blind spot on what happens with the disk around the more massive stars. So we would like to find out, of course. And these more massive stars are so-called Herbig ABE stars, which were suggested as a more massive counterpart of the T-Tauri stars. As the name suggests, the spectral type is A or B with emission lines, but it is often extended to include up to spectral type of F8. The spectrum should have infrared access due to hot or cool circumstellar dust. And in other words, it needs to be a disk. And they are typically young and moderately massive stars. And lastly, they are often divided into two separate groups. Group 1, which is interpreted as being a flaring disk, and group 2, which is being interpreted as a flat or self-shadowed disk. We know that planets do form around these stars. This is one of the most famous examples, HR 8799, around which 4 directly imaged exoplanets have been found, and this is a former Herbig star. And all 4 of them are at large distances and are quite massive. It is still unclear how these planets can form. From exoplanets, we also know that massive exoplanets are more common around massive stars. And in this figure, you can see that there's a clear increase in occurrence rate for stellar mass of these massive exoplanets. And we would like to know what is happening around these more massive stars. And a good first step to do this is to do a population study on Herbig stars with ALMA. So what do you do when you don't have any time on ALMA? Well, luckily, the ALMA archive is a treasure trove full of useful data. So we started from Viocatel 2018, who identified 252 Herbig stars in total. On the right, you can see a histogram, and the gray histogram is this survey. And to have a well-covered sample, we limited it to a distance of 450 parsecs, which nicely includes Orion, and which is the peak at 400 parsecs. And of these Herbigs, 36 have ALMA archival data. Here you can see all of them. You can see quite a variety of shapes and sizes. Asymmetry is rings, and some of them are not resolved due to relatively low resolution observation. But we can relate this millimeter flux coming from the disk to the dust mass with this simple relation here. A few assumptions are made. First, the emission is assumed to be optically thin. So in a way, all mass measurements are lower limits. Second, a particular power law index for the opacity is assumed. And lastly, the disk temperature is scaled with the luminosity of the star. These Herbigs are quite luminous, so the dust temperature is then around 60 kelvins. Also, the way how we compute the fluxes, we also get a measure of the disk size. Here you can see a cumulative distribution of the dust masses in the Herbig disks in blue, the relatively young star-forming region lupus in orange, and the older star-forming region upper skull in green, both of which mainly contain T-Tauri stars. And we find that the Herbig disks are 3 times more massive than the disk in lupus and 7 times more massive than the disks in upper skull. We can also fit a log normal distribution through these cumulative distributions to obtain these probability distributions. And here we can clearly see the differences in dust masses, and also that the Herbig dust mass distribution is narrower than for the other two. So there's a smaller range in possible dust masses, which is likely linked to the smaller range in stellar masses. We can also do something similar with dust radius. So here you can see a cumulative distribution for the dust radii. And because quite a few of the disks in lupus are unresolved, we can clearly see that most Herbig disks are larger than the T-Tauri disks. However, this is sort of the most positive distribution, let's say, for the Herbig disks, as there still are some unresolved and unobserved disks. We can sort of unbias this distribution by assuming that all unobserved and undetected disks are as small as the smallest in our sample. And this shifts the distribution, the dark blue distribution, towards the light blue one. And then you can see that's quite similar to the distribution of the disks in lupus. So only in that case, the two cases are quite similar. But the real distribution likely lies somewhere between the dark blue and the light blue distributions. We can combine all of this, the size and the mass, into one big plot. Here you see the dust mass on the x-axis and the radius on the y-axis. And the blue markers here are the Herbigs with upper limits and detections on the radius. And the gray dots and triangles are from Van der Marel and Mulders, who combined the radii and masses of a total of 700 protoplanetary disks from different works. And here you can clearly see that the most Herbig disks are larger and more massive than the most of the T-Tauri disks. There are still a few which are quite as large and massive, such as IM Loop and V1094 SCO, both of which are actually the largest T-Tauri disks in lupus. But the Herbig disks are larger and more massive than the bulk of the T-Tauri disks. We can also divide these Herbigs into the group 1 and group 2 sources, and we find that the group 1 sources are generally larger and more massive than the group 2 sources. Here you can see a cumulative distribution. And again, we can divide this into a probability, we can change this into a probability distribution, and we can clearly see the differences between them in masses. Moreover, the group 2 sources distribution of the group 2 sources is very similar to the one of the disk in lupus. If you look on the right figure on the right again, you can also notice that there are a few disks which are in group 1 and group 2 sources, which are very similar in both size and mass. And as a simple exercise, we can compare 3 pairs of these group 1 and group 2 sources. Here you can see 3 group 1 sources, and they all have a large ring with almost no mass close to the star. While for the group 2 sources, more mass is concentrated towards the star. I'll come back to this later. So there are 2 key results in our work. First, Herbig disks are more massive than T-Tauri disks, and second, Herbig disks are larger than T-Tauri disks. And what could be the origin of this? Well, there might be a link to massive exoplanet formation. For higher mass stars, disks will form around it containing more mass. So these disks can form massive exoplanets at larger distances. stopping radial drift of dust at larger separations from the star. So consequently, we find a larger disk and a higher inferred dust mass because of it extends larger on the sky. While on the other hand, a lower mass star forms with a lower mass disk, which will be unable to form such an exoplanet at large distance. So the dust will drift inwards, and we infer a lower dust mass and a smaller disk as well. Of course, the left case could also be a lucky star, so to say, and the right case an unlucky star, because we still find large T-Tauri disks and small Herbig disks. Going back to the group 1 and group 2 sources, the left case might be mostly the group 1 sources, where the inner disk has drifted inwards while there's a large ring left over. And the right case is group 2 sources, where most mass is concentrated closer inwards to the star. Lastly, because of how we measure these dust masses, these differences between the left case and the right case will become larger over time. Which is exactly what we see happening in the stellar mass dust mass relation, where this relation steepens over time. So the smaller disks become more optically thick over time, while the larger disks we still infer quite high dust masses. So in summary, we find that Herbig disks are more massive than T-Tauri disks, and that they are larger than the bulk of the T-Tauri disks, and that this can be explained by exoplanet formation at different separations from the star. Because of how we obtain these flux observations, disk evolution enlarges these differences between the disks as well. Thank you for listening to my presentation.